some allergies, so I might mute.
Okay, I think I got that started. Okay, let me do a little quick intro here. Welcome everybody to the AMSAT Engineering Update webinar. Your panelist for today's webinar is Jerry Buxton, N0JY, AMSAT's Vice President of Engineering. Please use the Q&A function to post any questions, and we'll get to those at the end. Is that okay, Jerry?
Yes, it is. I was just pulling up that screen there, so go ahead.
Okay. And then let's see, it's also being live streamed to YouTube, being recorded for later viewing, and you can find that information to access those videos at www.hamcation.com. Also, please know that your cameras don't need to be on and your microphones are all muted at the moment. And also, as we just said, there's a strict time limit to get started for the next webinar. So Jerry, you want to go ahead and get started?
I will. And good afternoon, everyone, or I guess since it's virtual, could be good morning still. I'm Jerry Buxton, Vice President Engineering, and I apologize for the delay getting in, but I'm going to use the show and we'll go through it maybe a little quicker than I thought. As you can see, for Hamcation, I decided that cruise is a good vacation, especially since it's snowing outside right now in North Texas, which is a little bit unusual. Here we go. I thought I'd start out with what AMSAT Engineering is, who we are, and it's a group of amateur radio operators, just like all others that are probably on here, or maybe there's some that want to be hams. There's a lot of fields in the amateur radio hobby that you can get involved in, and we all take a common interest in satellites and space. The people that work in engineering are skilled in various fields that are applicable, such as radios and power and IHU, which is the MCU, the computer that controls it. And through our shared desire for making such things, we get together and we make the satellites. And as is common with a lot of amateur radio projects, it's available to everyone. And the people that are working with us are also something that is really so behind the scenes you may not notice it, but extremely dedicated to what they're doing. There's a lot of strict requirements for getting even integrated for launch. And if you don't meet those requirements, pardon me, they're based around safety, especially for the launch vehicle. Once they deploy you into orbit, whether your satellite works or not, they certainly hope it does, but the contractual liability ends at that point. It does take long hours to do this. It can be less hours if we were to have many more volunteers, but because of the combination of the long hours and the long lifetime of a satellite, from design to integration can be 2-3 years, or maybe a little more, depending on the complexity of a new design. And everybody has a wonderful team atmosphere. They love to work together in teamwork, and that includes myself. I have always seen myself in my career as maybe I'm the boss, but I'm actually just a team member who gets to make some unpopular decisions sometimes. Here are a few photos of some of our engineering team. I had tried to round up as many as I could, but it was kind of short notice, and so I was only able to get a few of them together. And you can see we come from all over. You may recognize some of the names. These are really the people, these and the unseen ones are the people that make this go. I just make sure that it all comes together to be able to go. So a lot of paperwork, in other words. So what do? We build satellites, of course, which includes prototyping, designing, and then documenting it. Documents are a big part of what's going on, and not always popular with, in general, I think a lot of people, there's people that love it, but I think that engineers tend to prefer to do something than write it down, I guess. So we've made a great improvement over previous iterations of satellite building engineering, and all of this gets archived, and that's very important because it gives us a record to look back on when you're working on future satellites, such as we did to look back at AMSAT and some of the others in the AMSAT records. So the documents include ConOps, which is the description of what your plan is, your desire, and then system requirements set down what needs to be done, what requirements need to happen in order to make that work. Interface control documents are another aspect of it. That's for each of the systems to be able to fit together and talk together on the bus. And then, pardon me. Oh, through the construction, yeah, we've got various phases. I don't know if you can see my mouse on the screen, but just kind of starting at the top left image and then walking your way down there. We're looking at various photos from the different Fox satellites and some of Golf. So we have flat sat construction, which is actually where we take the satellite bus, which is typically stacked up, and lay it out flat on a desk. That way you can test it all together, and you can also be able to access different test ports and such that are there. You've got the engineering model phase, and that is a picture of Fox 1A engineering model as I received it and was working on it. And that's the stack I was talking about. Then, of course, you've got the finished product, if you will, the flight model sitting there. And it goes to environmental testing, which is shake and bake, as we call it sometimes. It involves vibration and possibly shock or acceleration, as well as a bake out, which is the bake part, in order to remove any foreign material, that is on the satellite, because when it gets to space, it will outgas that material and it will get everywhere. That can be a problem, especially if you have a camera and the like. As we go through this process of putting them together, there are a couple of key things along the way. Of course, that's the preliminary design review. So once you've gone through the prototype design documents and put together the engineering model, you're getting ready to put together the engineering model, you have the preliminary design review, then you proceed with the engineering model, have a critical design review in order to determine, is this going to work? Is this it, before we commit everything to it and build the flight model. After that comes the delivery and integration. I did mention environmental testing. Yes, sorry. I'm trying to speed it up, so I'll get on beam here in a second. Integration is the final step that we actually have our hands on the satellite. And what we do is we work with the APIC, the integration coordinator, as well as the launch vehicle sometimes, representatives from the launch vehicle, and put the satellite into the P-pod or whatever the dispenser is going to be that'll be mounted on the rocket. And then they subsequently hook that up with the rocket. And you can see a nice shot of that at the bottom picture there. That was the group of P-pods that flew Fox 1A. It's AO85 on the rear end of a Centaur second stage. So that was quite a ride there. A few photos to walk you through what it does, and then off we go. So some background on what we are working on, CubeSats. CubeSat was a coordinated design idea that took the best look at something that can be small, lightweight, and relatively cheap, and standardizing it so that it can be deployed from a number of different launch vehicles. In the past, especially with AMSAT, we would build satellites to fit the shape of the hole in the rocket, essentially, for rides. And in this case, we're still doing the same thing, but the hole is standardized. You have, as the Foxes are, a 1U CubeSat. 1U CubeSat, as you can see here, is about 100 millimeters cubed. There are a couple of exceptions to that, of course. There's the rails. These prevent the CubeSats from touching. They also contain some switches to signal when the satellite is separated from the others and from the deployer, as well as some springs to give it a little extra kick, so that the satellites, the CubeSats themselves, separate from each other as they come out. This is all from a CubeSat design specification. Cal Poly is the one who writes that, and it is used as the standard for CubeSats up to 3U. Here we have it 1.5U. Now the 1.5U is made so that you could put two of them into a typical 3U P-pod or dispenser. It's the same idea as the 1U. A 2U is more or less two 1Us stacked up. And then we get to the 3U, and the 3U is what we're talking about for the Gulf Series satellites. So it is as big as you can go into one dispenser at a reasonable price for what you get on a sponsored launch from NASA for the amount of money that they will allow or they grant to us. It is the maximum size for going to LEO. Pardon me. The AO92. AO92, excuse me, RADFXSat-2 was a 1U. This was a partnership with Vanderbilt University, ISD, Institute for Space Defense Electronics. And in this case, Vanderbilt University submitted the CSLI proposal, which is the selection process to look for a free launch from NASA. They submitted that in 2015. They had flown with us previously on Fox 1A, the very first one. So they submitted two proposals actually to partner together, and that was RADFXSat, which is AO91, and now RADFXSat-2, AO109. The experiments that they have on board measure low energy proton events, and that is an upset type situation. They use various semiconductors on experiment boards, and essentially in the low Earth orbit, your typical events are going to be low energy proton. Sorry, and that's what they're looking for. They're going to try to take that out and look at what type of upsets happen to what type of material and how often. And that is in conjunction with looking at and qualifying commercial off-the-shelf parts to be able to fly in space so that people understand what the characteristics of them are for various orbits, various radiation exposure. And that helps us a lot, of course, because we're looking for cheaper satellites, if you will. AO109 launched on January 17th on the Virgin Orbit Launcher 1. That was a fun launch to watch. We got to see it on I guess, a private view versus what the public was seeing at the time. Not the same as being there, but the cameras they had did a pretty good job of it. And as you know, if you've been following along, once we were deployed, the first thing that should happen after about 55 minutes is we will hear a beacon signal, and we did not hear that signal. So as we looked at what was going on, we started through our steps to qualify it on orbit. We realized that there is a weak signal from the transponder, but it's apparently not processing commands, or if it is, we can't see the response to it because we don't see the beacon. That's the primary one we want to get, because the telemetry contained in the beacon is everything you need to know about what's working or what's not working, and just as important or more important to be able to try to get some of the science. So in pursuing that, can't click a mouse today. We've got several options or possibilities that we've been thinking about as far as what might cause the problem. We have the receive antenna broke off. That's kind of the starting point, kind of like, you know, is your television plugged in is the first thing you might look at. That would explain it not receiving commands. It could be broken off. It might have not deployed fully. It is the 2-meter antenna in this case. Therefore, it's about a 24-inch wire that is wrapped around, as you have seen in some of the photos, or you will see in the upcoming photos. And when that 55-minute timer goes off, that antenna is deployed, and it should stretch out to be its full 24 inches. It's possible that it got hung up. It's possible that the wire did not melt when the burn resistor went off. However, in the testing and the design, we would expect that it should at least hear our command stations sending commands with the power levels that they have. The transmit antenna may also be an issue. The weak signal on the downlink of the transponder could be accounted for by that. The absence of a beacon kind of points away from that, though, because we should be able to hear some beacon
This is the moderator. Can anyone hear me? Okay. I'm trying to work the issue. It looks like it's on Jerry's side. Hang on a second.
Can you hear me now?
Yes, I can hear you now.
Okay, I don't know what Zoom had a little brain fade there, I guess you might say.
Okay, we got you now.
I don't know if I'll get the camera back or not, but I can still keep talking.
Yep, we got you on audio, so you can proceed.
Can you give me a quick where did I cut out?
You were talking golf.
Okay.
Go back a page, I think, or two. See where you were at.
Let's see, here we go. Finished up the rat effects anomaly. If I was talking about golf, it was probably just the slide where we were just.
Yeah, you were talking about the antenna and stuff going in and out. So that was the slide you were on.
Okie dokie. Here we go then. Golf is stands for greater orbit, larger footprint. These are 3U CubeSats. Golf T currently under construction with a launch manifest pending, which means that looks like we will have a ride on a rocket, but I have not signed paperwork for that yet to make it official. And we also have Golf 1, which is intended to follow a year or so after Golf T. Golf 1 will incorporate what we learn in the development and construction of Golf T, as well as hopefully a little bit what we learn on orbit. Golf 1 would be our first full pass at a golf satellite. Golf T, as you can see in the drawings here, I'll go over some of the systems that are obvious, if you will. It's going to have two UHF transmit antennas. One is for the transponder, and one is for the RT-IHU, the radiation tolerant IHU, has its own communication system to be able to be accessed directly for commands. We've got deployable solar panels. This is something new for what we have done. And you need more power, the more radios and stuff that you pack into a satellite. And of course, as we go higher and higher, we're going to need more power in general for everything. So this is our first step at making deployable solar panels. These would open up, and as you can see in the picture, there are also still panels on the back side. If they did not open up for some reason, we would have solar cells, solar panels all the way around the satellite. So it would be able to have some power, not nearly the max that we want. We have a multiband antenna that it folds out from the side there once we're on orbit. It's intended for picking up GPS for use by the SDR and by the guidance system. It is capable of receiving L, S, and C bands, and this is part of the development toward Golf 1, which would use 5 and dime, that's C and X bands. And it's also got a little pickoff for the 70 centimeter downlink signal. And we're hoping that we'd be able to operate while the transponder is operating in its nominal 2 meter up, 70 centimeter down. We can make it also be able to operate 2 meters up and X band down on the 10 gigahertz. This is the VHF 2 meter receive antenna. Similar to the Foxes, all these VHF UH antennas are wire that deploys once it's on orbit. And then there we go. We've got the X band antenna on the bottom. And that's just a patch antenna, a patch array of 4 elements currently is the design. That will be, of course, the nadir or earth pointing end controlled by the attitude control system. And the goals for Golf T are to test and qualify this new attitude determination and to test the deployable solar panels, radiation tolerant IHU. These are all new technology, if you will, to us that were actually developed by the AMSAT, the Skunk Works team over the past several years. And the attitude determination control is not ours, but it's something we're going to be purchasing. The solar panels, radiation tolerant IHU, and the SDR with 10 gigahertz downlink, those are all developments that come out of the think tank. They're going to have additional systems on it. We're going to have the Fox 1 IHU. So the IHU that has flown on all the Foxes and has proven to be reliable in LEO and capable of surviving resets such as South Atlantic anomaly is there because the RT-IHU is under test. If the RT-IHU has a problem, then we need to be able to have a backup. Speaking of backups, how's that? Kind of cheesy, but I switched to my webcam there. And then we've got the Fox 1E transponder, the legacy, we call them. That's going to fly as the backup to be able to handle commands and such. SDR also being tested, also new. But this will provide the VHF, UHF transponders that everybody's used to and the typical ham access for a LEO satellite. Here are some photos then of the development going on. That, sorry, I have to get close to read it. That's the RT-IHU, some testing and development going on there. Another shot of that. Here we have the SDR being tested with various configurations. And also on my YouTube and AMSAT's YouTube from Symposium last year and even the prior year, there are information in there, more particular information about the SDR and such. Here is what the signal looks like on Fox-to-LEM. So this is testing done in the IHU and beacon modulator. And yeah, I can't read it, I'm sorry. Anyway, more bench testing here. Here we go into a bit of the control swap between the IHU and the RT-IHU. And we'll move on to Golf 1. Golf 1 then, same basic design as Golf T, improved upon to the points that we can. Golf 1, as part of the Golf program, the plan is to go higher to higher orbits, develop the systems and the components and the experience to be able to handle the higher radiation environments. Because when we get out of LEO and start stretching up toward HEO and such, you start passing through some really nasty radiation. So Golf 1, we envisioned several years ago to be able to go up to an orbit somewhere around 1,200 kilometers. In other words, that would be in the neighborhood of AO7, FO29, and to be able to be there for a replacement, as well as for us to be able to learn the environment at 1,200 kilometers. That Golf 1 will carry a STEM camera experiment, as well as Vanderbilt University's experiments. They're always a good partner for us. And again, that's where we get a lot of our help on determining what types of components to use and such for the radiation. We have further qualification of the RT-IHU, but this is where we expect it to be, fully qualified to be able to handle things, because the RT-IHU provides a redundant processing path that we hope will help combat single event upsets and such as we get to the higher orbits with more radiation. The SDR again will fly with full 5 and dime this time, and that would help to be able to provide a high-speed downlink for the camera and the ISD experiment. the legacy Fox 1 IHU for backup and the legacy linear transponder for backup. Currently, that's the plan. Depending on how things actually fall out with Golf T, of course, hopefully nothing falls out, but we may not need those. But it's always good to have a backup. That would be an excellent backup. Those things have the heritage so that we know we can at the least command and get a beacon. And so that's what they get to ride along for. If we don't have the need for them, that does free up space for other stuff to fly. We have some challenges here, not the least of which with Golf 1 and everything else is the orbital debris compliance. Currently, with the 3U satellites, pardon me, we've got kind of a limit of about 600 kilometers of orbit. The configuration with the deployable solar panels is interesting because of the drag. So the orientation of the satellite, depending on what the orbit is, sun synchronous or not, it all varies depending on where those solar panels are going to be pointing in relation to the path of the orbit. And so they can go as little as, if it was coming in on straight at you, it would exceed 25 years at 600 kilometers. The 25-year rule, the orbital debris, means that we have to be able to deorbit within 25 years after the end of mission, which is currently held to be 25 years after launch by those who regulate that. So that's why we're kind of stuck so low. We would like to be able to go higher, and theoretically we could, depending on the orientation of the satellite. But you always have to use the worst case when you're evaluating what you can or will be able to do for a launch. The student camera experiment, there was a school system that was originally lined up, I think as far back as 2017, right around the beginning of the golf project anyway, to be the ones that would do the science for the camera. The camera was to be provided by one of our partners. However, the school system walked away from it, and the hardware support is in limbo at the moment. So we're going to be looking for someone else to be able to fill that hole. It's a key thing for getting the free launch that we got with the CSLI, because the education and the STEM education and such is always one of the big things that NASA is looking for. The SDR with full 5 and dime, I mentioned that. And the challenge of not being able to go above 600 kilometers or so is that's a pretty short orbit, especially when you get to the bigger area, like of a 3U satellite. Many of the CubeSat missions are satisfied with having a short orbit like that, but we like, of course, to go places you can't go now, but we're working on it. Currently, it would cost money to buy commercial parts that are approved, and that means that they're more expensive by the regulators as far as being able to be high reliability, that they'll be able to get us deorbited. The experiment, we have some other schools in mind or other opportunities to go with that as far as the educational part, as far the production of a camera or what camera we fly. There's a GoPro option. GoPro is going to be used on some of the Eric's missions, and so it has been flown to Mars. There's no reason that we couldn't go with a GoPro, although the original intent was something specifically for what the original school system wanted to do. And so taking that all into account, we're still pressing hard to go higher, and it will happen, just not the way that we originally had thought it would. The orbital debris kind of closed that down rather quickly. So as Robert did mention, we keep pushing along with the Golf program higher and higher and up to HEO, highly elliptical orbits. This is, if you were around at the time or aware of, the realm of the AO10, AO13, AO40 type phase 3 satellites and such that have an apogee that's up above the geosynchronous orbit belt. So it's above roughly 23,500 miles, I believe it is. And a perigee that's then down around maybe 800-900, just enough to keep it from burning up and re-entering too fast. The benefit of the HEO is that you get nearly hemisphere coverage from that height. And because the orbit is not synchronous, it will have an apogee at various points around the Earth over a period of a week or two, perhaps. And that allows hams from anywhere to be able to look over a hemisphere, which also means that you get near worldwide coverage from your own location. They have to be about right at the horizon in order to talk to the antipode, but still, it provided a lot of DX at the time, and that's where we're headed right now. There are launch opportunities for these through GTO flights. GTO is when they put a commercial satellite up into a geosynchronous transfer orbit. It's headed for the geo belt, and they launch it with a high perigee, low apogee, and then the satellite itself moves itself up to a circular orbit and inserts it into its little slot there in the geosynchronous belt. It's a lower cost to go with a GTO, which is nearly equatorial as far as inclination, versus looking for something such as a Molniya or other specific inclinations. I'm sure that you could probably find one as a ride share, but they're not nearly as common. And of course, common is better because it gives you more replacement opportunities, more frequent launches, and it's also lower cost. So with that, the HEO5 and geosynchronous orbit, because there are multi-million-dollar satellites up there that don't want to have anything to do with pack all that into it, and mass means size means cost as well. There is an opportunity that AMSAT has tried several times for a hosted payload where we would ride along on a commercial satellite, and we don't have anything like that underway right now. Our ears are always open, if you will, eyes and ears, so that I don't have anything to say that specifically. I know this will be a question. Why HEO instead of GEO? It is simply a matter of being able to get to that. GEO is going to be difficult because of the cost, because of the regulatory problems, and because of the involvement to be able to get 3 of them up to be able to cover the world, if that's the intention. So it's not that we're not ignoring GEO. I mean, like I said, AMSAT's worked on that for several years. It's just been difficult to have it come to fruition. So here's a few other mentions about it. There's one thing that really, I guess, is a good part to close, and that is the man behind the curtain. I titled it late at night last night. But the risk tolerance. The risk tolerance is really what decides everything we do, all in all. That's what I get the big bucks for and get to make the unpopular decisions sometimes. So how much risk are we willing to take to do this, to keep our volunteers? I mean, you can't work them to death. You can't flog them. I found that out. And you can't fire them. So there you go. But seriously, it takes a lot of work to do this. So you have to be cognizant of what the people's saving money. That too, I mean, you can go out and buy some pretty dandy satellite parts and make a pretty dandy satellite, and that lowers your risk. But how much risk do we want to do that in saving as much money as possible? The Gulf satellites are going to be more expensive than we've ever spent on anything, at least in my 10 years of doing this. And so, that it has been brought up. Why is the price going up? Well, because it has to. We want it to work. We got to concentrate on covering some of that risk. Buying launches, maintaining an image. In other words, I'm saying here that it's easy to say pie in the sky, we're going to do this for the membership. And I know I just talk honestly. What can I say? But the fact is, it doesn't pay off if you can't deliver what you say. It makes no sense to say, we're going to do this. We're going to have like Golf 1 up there at 1,200 kilometers in a year, and then either achieve it by cutting all sorts of corners or fail it and you look dumb. And then the key question is,
hey, Jerry, we're running out of time here.
This is the last one. How much risk do you think is inherent in the volunteer built satellites? Like right now, multiple choice, some risk, lots of risk, not much risk, or it's absolutely the highest risk to every mission we undertake, which is true. And that goes into the CSLI to NASA. Tony Montero recognized it on the first one, and it is a fact that our volunteers come and go, and therefore it creates the highest risk. What we do is we do the best we can to manage that risk and be able to achieve the goals that we set. And with that, should we do it? It's up to you, Mr. Moderator, how you want to proceed here.
Why don't do you have a email address you could send out that people could ask their question to, since we got a late start and kind of ran out of time for the Q&A section?
Yeah. Give me 1 second. I just need to remember it exactly. Okay. The email address would be engineering, just like it sounds, engineering@amsat.us. And note the .us, not .org. Engineering@amsat.us will come directly to me, and I'll be able to answer questions there to the best that I can. And what I might offer real quick, if I could do it, is that if you have the opportunity, and I'd like to do more Q&A like I did a week ago, live and gather. So getting people together to do just that for a half hour or something is fine with me. And I appreciate the time. And as short as it was, I'm sorry I got a little rushed there trying to fit it in, but I hope you got the idea. There's many videos on my YouTube channel. And thank you much.
Hey, thank you. And with that, sorry we didn't get to the questions and answers, but email those to that address Jerry mentioned, and also you can revisit any of the sessions on the YouTube Stage Tech channel. All right, thank y'all.